Have you ever stopped and wondered how gravity actually works? How it pulls you down without anything physically touching you? Or how a magnet snaps to your fridge right through a piece of paper? It kind of feels like magic, right? But it's all science. And what if I told you the answer to both is pretty much the same thing? It's this invisible architecture that shapes our entire universe. And today, we're going to map it out. And to get our heads around this, we are going to start with a pretty weird question. Is a stink field a real scientific field? Yeah, I know, it sounds completely ridiculous, but just stick with me here, because this is honestly a brilliant way to understand a really fundamental concept. Come on, we've all been there. You're walking past a garbage can on a hot summer day and yuck. You don't have to touch the garbage to know it's there, right? You're reacting to something that travels through the air and hits you from a distance. So this is our starting point. And the stink field, it has rules. The more garbage you have, the stronger the smell. The farther away you get, the weaker it is. And on a really hot day, that whole zone of influence gets way bigger. Just keep these simple rules in your head, because they are the key to understanding much, much bigger forces. Okay, so let's pivot from garbage to the entire cosmos. That very same idea, influence at a distance, is the exact puzzle scientists were trying to solve for centuries. A ball falls, a paperclip jumps to a magnet, but there are no invisible strings pulling them. So what in the world is going on in that empty space? Well, the answer they came up with has a name, a non-contact force. It's really just a push or a pull that can work across empty space. Gravity and magnetism are the classic examples, of course. And this idea, this concept, forced us to invent a whole new way of thinking about how the universe works. And that new way of thinking is the scientific field. Now, we're not talking about a field of grass here. Think of it more like a field of influence. It's the area, the region of space where one of these non-contact forces can actually be felt. So the Earth, for example, generates a gravitational field all around it, and pretty much anything with mass that wanders into this field is going to feel its pull. So how do you draw something that's totally invisible? Well, scientists have a couple of tricks up their sleeve. On the left, you've got force arrows. These are awesome for showing the specific pull on one single thing, like the tiny little tug on a leaf compared to the much stronger pull on a big dog. But to see the whole picture, we use what are called field lines, like you see on the right. They let us map the entire invisible architecture of that force. Okay, so now that we've got the basic idea down, let's take a little tour of the three most fundamental fields in our universe. We're going to start with the one we experience every single second of every day. Gravity. Okay, here's the most important part. Literally anything with mass, you, me, this planet, the sun, creates a gravitational field. It's always attractive, it always pulls things together, and its strength just depends on how much mass there is and how far apart things are. The sun is so unbelievably massive that its gravitational field is strong enough to hold our entire solar system together in this huge cosmic dance. All right, next up on our tour, a field that's a bit more dynamic. We're moving on from the steady, constant pull of planets to the sudden zap of static electricity. Let's dive in to electric fields. Now, unlike gravity, which only pulls things together, electric fields can both attract and repel. Their source isn't mass, it's electric charge. You know the old saying, opposites attract, so a positive charge pulls on a negative one. But two positive charges, they're going to push each other away. You feel this all the time with static cling when you pull clothes out of the dryer. That's literally just electric fields pulling your sock to your shirt. And for our final stop on the tour, we've got the force that guides compasses, sticks things to our fridges, and pretty much powers our entire modern world, magnetism. Magnetic fields should feel pretty familiar now because they follow the exact same rules as electric fields. They're just created by magnets that have north and south poles instead of positive and negative charges. Opposite poles attract, like poles repel. Simple as that. Our whole planet, in fact, generates a massive magnetic field that protects us from space radiation and even helps animals navigate across the globe. Okay, check this out. This rule applies to all three of the fields we've talked about: gravity, electric, and magnetic. Look at this table. At 1 meter away, let's say the force is 100 units. Now, just double that distance to 2 meters. The force doesn't get cut in half, oh no. It absolutely plummets all the way down to 25. This rapid drop-off is a universal law for these invisible forces.
Yeah, that's a 75% drop in force just by doubling the distance. It's not some gradual decline, it's like falling off a cliff. And this is exactly why a small magnet is super strong when it's right up close, but you can't feel it at all from across the room. The influence of these fields just fades out incredibly fast. So we know what these fields are, we know how they behave, but why does any of this matter? Well, it turns out these invisible forces don't just explain how the universe works, they're what make it spectacular. And by understanding them, we're starting to build some absolutely mind-blowing technologies for the future. Just think about it for a second. Earth's magnetic field creates the beautiful northern lights and lets sea turtles navigate entire oceans. The electric field in our atmosphere gives us lightning. The sun's gravity gives us a stable home in the cosmos. And at the most extreme end, the gravitational fields of black holes are so powerful, they literally bend the fabric of space-time itself. And this isn't just about cool nature facts. It's about changing our future. Get this. Engineers are already figuring out how to weaponize magnetic fields against diseases like cancer. Imagine injecting a patient with medicine that's bound to tiny magnetic particles. Then you use a powerful magnet outside the body to steer that medicine exactly to a tumor, leaving all the healthy cells completely untouched. That is the power of harnessing these fields.
Okay, what an incredible journey through these invisible forces. But now, it's time to go all the way back to where we started and answer our original, weird question once and for all. So let's look at the side-by-side comparison. Our stink field actually behaves a lot like the real ones. A stronger source, more garbage, more mass, more charge, creates a stronger effect. And in every single case, the effect gets weaker with distance. The analogy holds up really, really well, but only to a point.
And here it is, the crucial difference. A stink field is not a real scientific field. So why not? It's because the smell is carried by actual physical particles, molecules from the garbage literally traveling through the air to your nose. A true scientific field, on the other hand, is a fundamental property of space itself. It is the force. It's not just something carrying the force. And just when you think we've got it all figured out, science throws us a curveball. New research is suggesting that the crazy intense gravitational fields around black holes might actually make space-time itself bumpy, kind of like the surface of choppy water. It just goes to show you, our understanding of these fundamental forces is still growing, still evolving. So we'll leave you with this thought. We've mapped out gravity, electricity, and magnetism, but that doesn't mean we found everything. What other invisible fields might be out there shaping our reality in ways we can't even begin to imagine yet? The search for answers, as always, continues.